Hi, my name is Javier Gonzalez. I'm a principal software engineer with Samsung Electronics, and I lead Samsung Semiconductor Denmark Research, which is an R&D center in Europe where we focus on open source, ecosystem, and architecture for next generation SSD interfaces. I'm happy to be part of this OCP 2020 virtual conference. This year is a little bit different than others, but it is great to contribute to this initiative and continue to share knowledge despite the adversities. Today, I'd like to present you some of the work that we're doing in the context of NVMe zone namespaces. I will go through the use cases that we see you can benefit from this technology and then dive directly into our live demo or semi-live demo, where we will focus on looking at the write amplification advantages on CNS. If you want to know more about zone namespaces, the work we're doing, the extensions that we're working on, and what's our vision on the technology in itself. We do have some materials online. The most recent are from SDC EMEA on Vault 2020, together with a tutorial for FAST. And you can always reach out to us if you want to hear more specifics. So if we go directly into it, CNS is a new NVMe namespace type. Essentially breaks the LBA address space into zones of fixed size. And how these zones are mapped to the device and the relation between them is unknown to the host at this moment in time. What we have at the moment is that each zone is governed by a write pointer that needs to move incrementally. And we also have a state machine that allows a zone to transition between empty, open, close, and full states. And we also have a couple of exception states, offline and read-only. The important thing to notice here is that the state machine is managed by the host, which means that any mapping is done at a lower granularity than a zone. It is managed by host software. This essentially means that garbage collection is host-driven. So applications and file systems that are being around append-only data structures, such as log structure registries, can leverage their internal garbage collection and remove the indirection layer causing extra write amplification. This has an obvious impact on the WAF factor. And depending on how zones are laid out, it also has an impact on bandwidth and tail latencies. So let's look at two use cases and how the way zones are mapped can have a big impact on how CNS can be used. So the first use case and the most obvious one is archival. Here CNS presents a good way to consume a high density NAND like you'll see, as it helps to further reduce the total cost of ownership of the SSD. And we have three ways in which CNS helps. So first of all, CNS breaks the 1 GB per terabyte mapping table, which helps to reduce DRAM on the device side. Second, CNS helps reducing NAND over-provisioning. Since garbage collection is no longer managed strictly by the device, then we do not need to add extra blocks to maintain a steady state in terms of bandwidth and latency. And the host algorithms that are already taking place today take part of this load. In the third end, CNS helps lowering end-to-end write amplification. And this is because the data movement that typically takes place during garbage collection is no longer a 4K best effort, but instead it is integrated into the host data structures, which removes the level of indirection I was mentioning before. So CNS places itself for the archival case as a layer above the high capacity hard drives. There are some commonalities, especially if that layer is formed by a single magnetic recording hard drives or SMR. And we expect the software layer and the algorithms driving the archival CNS use case being very, very similar to those of SMR drives. The second use case for CNS is not that obvious, and I'm a big fan of it, is the IO predictability. Here we obviously inherit all the intrinsic CNS properties that we just described, lowering DRAM, lowering OP, and lowering end-to-end write amplification. However, the focus is not on the cold data, but on the IO separation as a means to provide a framework for predictable multi-tenant workloads. which is what in essence we typically refer to as the noisy neighbor problem. Here zones are smaller than in the archival case and are laid over a smaller number of dies on the NAND array. And they form what we are referring to as isolation domains at the moment. The host has visibility over these isolation domains and can make decisions on the bandwidth versus latency trade-off to better serve different workloads. Those of you that are familiar with open channel SSD use cases can see how this architecture covers these use cases and can help existing users transition to a standard NVMe solution as CNSs. At the moment today, CNS does not have the bits to enable isolation domains, but we are working into bringing this to NVMe at the moment. If you're interested in this use case, again, contact to us. Very quickly, in terms of software stack, I'm focusing on Linux. CNS builds on top of the existing zone block ecosystem that the community has been building for years to support SMR hard drives. And here you can see in orange parts of the framework extensions that we are adding nowadays on our own software stack. And as soon as the CNSTP gets ratified, we will start pushing this code upstream and obviously collaborate with everybody and other vendors and customers that are doing the same thing. I would like to drive your attention to a couple parts here before we move on. The first one is QEMU emulation. We have a fully virtualized environment for emulating CNS devices. This has triggered a big refactoring of the NVMe driver in QEMU. We have a bunch of patches already bringing QEMU up to speed in 1.3 and 1.4 NVMe, and we're in the process of merging them. This will be the base, or these are the pre-patches for CNS to be pushed as soon as it is ratified. Then we've obviously made changes to the NVMe driver, the block layer to adapt a couple of things, the new append command and the some random write area, which we're discussing now in NVMe. We have enabled IO uring, libeio, ioctos for admin commands. But the part that I'm very interested in talking about now is that library that sits right under Roxy that we call XNVMe. So XNVMe is a library made for simplifying NVMe native applications. XNVMe presents a thin API for applications and abstracts the transport backend. This allows to switch between backends, such as, for example, IO uring or SPDK at runtime without further application changes. So once an application uses or is ported to support XNVMe, it can also be used on different OSs there. So at the moment, we're focusing on Linux and FreeBSD, but we will enable other OSs if we see a customer base for it. We see XNVMe being useful for standard NVMe commands, and we already have customers looking into it from a simple integration perspective, wanting to move out from a specific backend and having more coverage without having code changes. However, it is when rewriting applications backends for new namespace types that XNVMe shows its true powers, right? Applications having support for CNS can use XNVMe to minimize changes and abstract the details of the CNS implementation and just focus on the data structure that can leverage this new namespace type. These applications will get direct support for different backends and can continue using the one that it used today, but they can also go and experiment with other ones. Since XNVMe is built on a standard NVMe, we have transparent support for fabrics. Again, here we have customers that see XNVMe interesting on the initiator side. Some others see it interesting on the target side, and we have a couple of customers that see it interested on both sides. There's other things that we've been working on, like tools like NVMe CLI, block zone, some file system tools. Those are also going to go upstream, and some testing in FI and block tests that also will go up as soon as we ratify the TPs. So Focusing on the demo where you're seeing here today, it's a RocksDB a workload that in a Rocksdb version that runs on top of XMVME, and right under XMVME runs three different paths. So in the first path, we do RocksDB XMVME IO uring through X4 and a conventional namespace on a traditional NVMe SSD. On the second path, we have again RocksDB XMVME IO uring on top of F2FS. We want to see this because F2FS, it is in itself a flash optimized file system. So since we're focusing on both seeing the right amplification factor introduced by the software and the right amplification factor introduced by the device, we want to see how software that is flash friendly introduces some right amplification benefits. The third path is RocksDB XMVME, but in this case, there's no file system. XMVME, the RocksDB backend directly uses XMVME to map data from SS tables to zones, and it goes to the block layer, NVMe driver, and CNS SSD. Coming back to what I said before, this version of RocksDB could perfectly run an SPDK without having any other changes on the source code of RocksDB. A thing to note here is that our conventional SSD and our zone namespace SSD are equivalent. Is our last generation enterprise controller, same next generation NAND. So everything is a really apples to apples comparison. So now let's dive into our Semilive CNS demo. It's obviously a recording, cannot go to the office nowadays and make a live recording of the demo, but this is the original video that we made as soon as we knew that we could not attend OCP in person. We will make the demo available. We're looking into ways in making it online so that it can run oh. Boom. So now let's dive into our Semilive CNS demo. Guess you all know we cannot go to the office and go record anything or make a live presentation. This is actually the video that we recorded of the demo on the day we knew that we're not going to be able to attend OCP physically to start with. We're looking for ways to make the demo available online so that you can run it and see the different parameters. But we'll announce when time comes. For now, you can see on the left hand side we have a terminal running different workloads of RocksDB. On the right hand side we have a Grafana dashboard with the three paths. So I'm going to describe what we're seeing and then make a couple of remarks on how to interpret the data. So the first thing I want to draw your attention to is the number in red. That's the X4 file system write amplification. This is write amplification calculated by number of bytes that are leaving a user space right under XMVME at a byte level, at an interface level, and a number of bytes that come out of the file system only for data, no metadata. So that is complete data write amplification as data is being written and then moved around because of the way it is being mapped on the file system. And the number in yellow is F2FS. And you can start to see the benefits of mapping data in a way that respects this sequentiality append-only fashion, especially if you're trying to match your device and you configure it properly to match your device super blocks or erase blocks, right? Note that F2FS in this case is vanilla F2FS running on log structure mode, but without the CNS or some block extensions. It's only running as a normal block device. On the green big number, you see the route amplification for RockCP running on XMPME and on the CNS backend. And here you see that we are orders of magnitude below in terms of route amplification. And actually, the numbers that you're seeing there, that 0.000059, is there because we have implemented the RockCP backend that sits on top of XMVME, but we have not optimized the LSM tree to take advantage of it. So we have not tuned how the mem tables in RockCP, the sizes when they need to be transformed in SS tables across a number of zones. And this means that we will have at the end of the SS tables a number of bytes that we need to pad so that we can close the SS table on the zone, and the other way around when we need to close the zone and to make sure that we can move data in chunks when RockCP garbage collection comes around, right? We did some of this initial work in the open channel context. And now that we have reached this level where we can have a stable implementation, we're starting to look at that again to optimize the LSM tree to work in a pen-only fashion within a constrained size so that we can really take advantage of CNS and take advantage of the zones. And this work will also benefit the implementations that might come for SMR drives. So that is the software layer. And this is an important thing because as we see the other layers of write amplification, note that in a specific moment in time, all write amplifications at the different layers need to be compounded. So the fact that you have a 1.1 write amplification at the file system layer, and then you have like a 2 point something on your RockCP workload, then multiplied by the number of the write amplification you have in a moment in time on your device, just because of the garbage collection on the device, that number evolves through time, but is directly affected as a factor. So just by reducing write amplification at a software layer, we are already making a huge impact. Now, if we move to the second layer where you see a CNS device controller and a CNS device controller, at this point, we do not want to discuss about the garbage collection impact on write amplification on a specific controller and NAND. If you're a big NAND controller user, SSD user, you probably know this number. Depends very much on the grade of the controller, grade of the NAND, the vendor, the workload you're running. Sometimes it can be just as low as under 2x write amplification. Sometimes, depending on the controller and on the vendor, can be as high as 4 or 5x, right? So just use that number there. And again, consider that it needs to be compounded with the software that you're using on top. For this particular CNS device, at this moment, we have a write amplification of 1. It is true that NAND is non-perfect. Some blocks can become back through time. That's no secret. So that number can increase at the 670 as time goes, but there is no continuous increase on write amplification due to usage because of our CNS implementation. So you can expect that number to remain very, very close to 1 in the 670 magnitude through the life of the device. And then the lowest layer, that's the RockCP LSM tree. That is the write amplification that RockCP itself is causing, and this is measured by RockCP metrics. We're not getting into that yet. That's the algorithm that is running. We might want to look into it into the future. Some other people are looking at all the data structures. What we're interested on is the comparison here that our software layer, the part that is the interface, the part that is what would be equivalent to the file system, the mapping to LBAs on the device, that has a big impact when using CNS. The upper numbers are for completion in terms of the number of IOPS we're running at a moment in time and latencies. don't pay too much attention to those because we have rate limited ROCCP. We do not want to talk about performance at this time. We do not want to have a comparison at this time. And we have rate limited so that both devices are not being compared. They don't suffer at this moment in time from being suffocated at any end. Again, if you want to hear our numbers and you want to know more about this, please contact us. So, a couple takeaways. CNS's new interface is being standardized in NVMe. It builds on top of the namespace types. The only one that is now out there is key value. Other things might come into the future, probably related to computation. It's driven by a number of vendors and early customers, which is a good mixture, and we're happy to get customers looking into it and giving us early feedback. That is helping both the interface and the product. CNS, from our point of view, targets two main cases. Archival, which is probably the original use case, but IO Predictability, we see it as a very big content for making a CNS successful. The CNS demo, you've seen how CNS helps reducing end-to-end write amplification, both at a device level because of the design of the CNS interface in itself and the actual implementation, but also at a software level due to removing of indirection layers. And this write amplification reduction applies to both use cases below. Yeah. In terms of ecosystem, a lot of people is contributing to it at the moment. We are also contributing to it heavily. When the TPs get ratified, we will push upstream our code to the Linux kernel, the different tools, libraries, QEMU. We're making XNVMe available in the next couple of weeks only for NVMe, standard NVMe, and we're also making available the CNS extensions as soon as we can. In terms of standardization, we're heavily involved in the CNS technical proposal in NVMe, and we're working in extending it to cover the use cases we believe it can be helpful with. If you want to know more, mention it a couple times, please contact us. We're happy to talk to you. And I guess that's it. Thank you very much for attending this virtual conference. Hope that we can see each other face to face very soon, and stay healthy. Thanks.